12 light years from Earth, orbiting a star you can see with the naked eye on a clear night, there's a planet 7.5 times the mass of Jupiter, a giant world so cold that water freezes in its upper atmosphere and forms clouds of ice that drift through its skies in thick, patchy layers. Nobody knew those clouds were there. The models said they should not exist. And then the James Webb Space Telescope looked twice, saw something that didn't fit, and forced the entire field of planetary science to start rewriting its assumptions about how giant planets work. And that is only the first story. Because at the same time, 190 light years away, a completely different JWST observation has cracked open one of the strangest planetary systems ever discovered, a Mini-Neptune orbiting inside the orbit of a hot Jupiter, two planets that should not exist together in the same system, whose atmospheres just revealed a secret about where they came from that nobody predicted. Two discoveries, two separate star systems, two completely different types of planets. Both were announced in the space of 2 weeks in April and May 2026, and both carry implications that go far beyond the individual worlds themselves. Implications that reach into how we understand planet formation, how we model alien atmospheres, and ultimately how we search for life beyond our solar system. Let's start with the frozen giant. The planet is called Epsilon Indi Ab. Its star, Epsilon Indi A, is a K-type star, slightly smaller and cooler than our Sun, located approximately 12 light years away in the southern constellation of Indus. At that distance, it is one of our closest stellar neighbors. Epsilon Indi A is visible to the naked eye from the southern hemisphere and has been studied by astronomers for decades, but nobody knew it had a planet until 2024. When JWST first directly imaged Epsilon Indi Ab using the coronagraph instrument on the telescope's mid-infrared instrument, MIRI. A coronagraph is a device that blocks a star's overwhelming light so that faint objects close to it, like planets, can be detected. Direct imaging of exoplanets is extraordinarily difficult because planets are billions of times fainter than the stars they orbit. JWST's coronagraph made it possible to isolate the planet's own faint infrared glow from the background starlight and detect it directly. What the 2024 observations revealed was already remarkable. Epsilon Indi Ab has a mass of approximately 6 times Jupiter. The 2026 study refined this estimate to 7.6 Jupiter masses, making it one of the most massive exoplanets directly imaged to date. Its orbital distance from its star is approximately 30 astronomical units, roughly the same distance as Neptune from our Sun. It is therefore a cold planet with an estimated atmospheric temperature of approximately 275 Kelvin, just 2 degrees Celsius or 35 degrees Fahrenheit. That makes it the coldest exoplanet ever directly imaged, and one of the most genuinely Jupiter-like alien worlds ever studied. For comparison, Jupiter itself has an atmospheric temperature of approximately 140 Kelvin, minus 133 degrees Celsius. Epsilon Indi Ab is warmer than our Jupiter, which astronomers interpret as a sign that the planet is still relatively young and still radiating heat left over from its formation. As it ages, it will cool further, eventually becoming more Jupiter-like in temperature as well as mass. The 2024 first observations detected ammonia in the atmosphere and produced a spectrum, a measurement of how the planet's light varies across different wavelengths, that gave the first glimpse of its atmospheric composition. But that spectrum left something unexplained. The planet appeared brighter than the theoretical models predicted it should be. The standard models of cold, giant planet atmospheres were producing numbers that didn't match what JWST was actually seeing. So the team, led by Elizabeth Matthews at the Max Planck Institute for Astronomy in Heidelberg, went back for a second look. The second visit, published in the Astrophysical Journal Letters on April 22, 2026, confirmed the ammonia detection. But more importantly, it provided the best explanation yet for why the planet was brighter than the models expected. The answer is clouds. Thick, patchy water ice clouds forming in the upper atmosphere of Epsilon Indi Ab and reflecting more infrared light outward than the models had accounted for. These are not water vapor clouds of the kind that form in Earth's atmosphere when liquid water evaporates and condenses. They are clouds made of water ice, frozen water crystals forming at the extreme cold of the planet's upper atmosphere, at altitudes where the temperature drops below the freezing point of water, and drifting in thick layers that partially obscure the deeper, warmer atmospheric layers beneath. The detection of these clouds was not straightforward. The atmosphere did not have enough ammonia to explain the ultra brightness enhancement on its own. The team's modeling work showed that the most physically consistent explanation, the one that could account simultaneously for the observed brightness, the ammonia abundance, and the spectral shape of the planet's emission, was the presence of thick, patchy water ice clouds at high altitudes. The word patchy is important here. Uniform cloud layers produce a different spectral signature from clouds that are distributed in irregular patches across the planet's disk, and the JWST data was more consistent with patchy clouds than with a uniform layer. This implies that the atmospheric dynamics of Epsilon Indiab, the winds, the convection, the circulation patterns that distribute clouds across the planet, are complex, variable, and far less uniform than simple models assumed. Elizabeth Matthews, the study's lead author, described the finding in terms that capture both its scientific significance and its broader implications. She said that JWST is finally allowing scientists to study solar system analog planets in detail, and that if an alien civilization several light years away were looking back at our sun, JWST would be the first telescope powerful enough to study Jupiter in the same way. She noted that what once seemed impossible to detect is now within reach, allowing researchers to probe the structure of alien atmospheres, including the presence of clouds, and that this reveals new layers of complexity that atmospheric models are now beginning to capture. That last point about models deserves emphasis. The water ice clouds on Epsilon Indiab were not predicted. The models that planetary scientists have been using to understand cold giant planet atmospheres did not include them as a significant factor. The planet was brighter than the models said it should be, and the explanation turned out to be a feature that the models had not adequately accounted for. This is how science actually advances, not through confirmation of what was expected, but through discrepancies that force refinement. The discovery does not just tell us something new about Epsilon Indiab. It tells us that every cold giant planet studied before JWST existed was being analyzed with models that were missing an important piece of physics. Every atmospheric analysis of a cold exoplanet conducted before JWST needs to be revisited with the possibility of ice cloud effects in mind. The team is already applying for additional JWST observation time to study more cold Jupiter-like planets. And NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2026 to 2027, is expected to be well suited for detecting reflective water ice clouds on cold giants, providing a larger sample of worlds to compare against Epsilon Indiab. The second visit to a single planet has opened a new chapter in how the field approaches the atmospheric characterization of cold giant worlds. The full implications of that chapter will unfold over the coming decade. Now for the second story, 190 light-years away, in the star system designated TOI 1130. This is a story about a planetary pair that should not exist, and whose existence has just been explained for the first time. The TOI 1130 system was identified in 2025 by researcher Chelsea Huang. It contains two planets orbiting very close to their host star, a Mini-Neptune and a hot Jupiter. The Mini-Neptune orbits the star every 4 days. The hot Jupiter orbits every 8 days. That makes the Mini-Neptune an interior companion to the hot Jupiter. It orbits closer to the star, inside the hot Jupiter's orbit. And this is extraordinarily strange. Hot Jupiters, massive planets orbiting extremely close to their stars, are considered solitary planets in planetary science. The reason is gravitational. A Jupiter-mass planet orbiting close to a star has such a strong gravitational influence on the surrounding planetary system that it typically clears out any other planets from the inner orbits through gravitational scattering. Hot Jupiters are overwhelmingly found alone. Finding a Mini-Neptune sharing the inner system with a hot Jupiter is so unusual that the very existence of the TOI 1130 pair immediately raised the question of how such a system could possibly have formed. The standard models of planetary formation and migration could not easily explain it. A team of scientists from MIT used JWST to analyze the atmosphere of the Mini-Neptune TOI 1130b, making it the first time astronomers had ever measured the composition of the atmosphere of a planet orbiting within the orbit of a hot Jupiter. What they found in that atmosphere is the key to unlocking the mystery of the entire system's origin. The Mini-Neptune's atmosphere is heavy, rich in water vapor, carbon dioxide, sulfur dioxide, and methane. This is a chemically complex, volatile-rich atmospheric composition that carries a specific implication. It is inconsistent with the Mini-Neptune having formed where it currently orbits, close to its star. Here is why that matters. Close to a star, in the region where temperatures are high and radiation is intense, the conditions during planet formation favor the creation of rocky, volatile poor bodies. The building blocks available close to a star are depleted in water ice and carbon compounds because those materials evaporate in the heat. A planet that formed close to its star should have a relatively simple, low metallicity atmosphere with limited water and carbon. TOI 1130b has the opposite. A high metallicity atmosphere heavy with water vapor and carbon compounds. The chemical fingerprint in its atmosphere is the fingerprint of a planet that formed beyond the frost line. the boundary in a planetary system where temperatures are cold enough for water ice and other volatile compounds to condense into solid particles and become part of the building material for planets. Beyond the frost line, planets can accrete large amounts of water ice, carbon compounds, and other volatiles. Inside the frost line, they cannot. The fact that TOI 1130b is now orbiting close to its star, but has an atmosphere chemically consistent with formation far from its star, means only one thing: it migrated. It formed far out in the planetary system in the cold, volatile-rich outer regions beyond the frost line, and then it moved inward, driven by gravitational interactions with a protoplanetary disk or with other bodies, until it settled into its current 4-day orbit. And here is the crucial implication for the hot Jupiter sitting just outside it. If the Mini-Neptune formed far from the star and migrated inward, the hot Jupiter almost certainly did the same thing. They both started their lives in the cold outer reaches of the TOI 1130 system. They both migrated inward together, and instead of the gravitational interaction between them resulting in one ejecting the other, as it does in most systems with hot Jupiters, these two planets ended up locked in a configuration that kept them both in stable orbits close to their star. The MIT team's results were published in Astrophysical Journal Letters in May 2026. The lead researcher noted that this is not just a story about TOI 1130, it is a template. Understanding how one planetary odd couple survived the migration process and ended up in its current configuration tells us something general about the conditions under which planetary systems can form multiple close-in planets rather than ending up with the solitary hot Jupiter that most systems produce. And the key tool that made this understanding possible, and the ability to measure the atmospheric composition of a small planet orbiting inside the orbit of a larger one at 190 light-years distance in enough chemical detail to reconstruct its formation history, is JWST. Nothing that existed before JWST could have done this. The Hubble Space Telescope, Spitzer, Kepler, none of them had the sensitivity or the infrared wavelength coverage to measure the atmospheric spectrum of TOI 1130b in the detail the MIT team achieved. Both of these discoveries, the frozen clouds on Epsilon Indiab and the migrating origins of TOI 1130b, are chapters in a larger story that JWST is writing about the universe planet by planet. When the telescope launched in December 2021, the planetary science community knew it would be transformative. But the specific ways it has been transformative have repeatedly exceeded expectations. The frozen clouds that the atmospheric models did not predict. The Mini-Neptune, whose atmosphere remembers where it was born. These are not the discoveries anyone specifically went looking for. They are the discoveries that emerged from the data when scientists looked carefully enough. And that is exactly how the most important science tends to work. The closest superJupiter to Earth has ice clouds. Its neighbor stars hosting a planetary pair that defies the rules of how solar systems are supposed to work. And a telescope the size of a tennis court, orbiting 1 million miles from Earth, is changing what humanity knows about the universe one infrared photon at a time.